Now let's calculate some definite integrals using the fundamental theorem of calculus, and I hope these examples will be enough to get you going, and of course if they're not, please let me know. So let's calculate the definite integral from 2 to 4 of x minus 2. All right, notice, by the way, we should think of x minus 2, this function here, as being multiplied by dx, and that's why the parentheses are around it, and why I have the multiplication symbol. And so let's see, the definite integral from 2 to 4 of x minus 2 times dx. Now remember, there's two steps. The first step is we have to calculate an antiderivative. So if I antidifferentiate x to the first, I get x to the second over 2 minus, when I antidifferentiate 2, I have to think what function has 2 as its derivative, and of course that's 2x. In definite integrals, we don't have to worry about a constant of integration. So now I've taken the antiderivative, but I haven't evaluated it. And remember, the second step involves evaluating it at these limits of integration. So I put it in square grouping symbols. Write the lower limit 2 at the bottom, the upper limit of integration 4 at the top. And now recall what this means. This means evaluate it first at 4. So that would be 4 squared over 2 minus 2 times 4. Then evaluate it at 2. That'd be 2 squared over 2 minus 2 times 2. All right. And then remember, after we evaluate it, subtract the value at the upper limit 4 minus the value of the lower limit 2. All right, so this is going to be 16. 4 squared divided by 2 is 8. So we'll have 8 minus 8, that's 0. Okay, and this will be 2 squared 4 divided by 2. 2 squared 4 divided by 2 is 2. Minus 4, 2 times 2. And so this is going to be 0 minus 2 minus 4 is negative 2. And that would be 2. All right. So the value of this definite integral is 2. Let's take a look at a picture. Here we have that function x minus 2. Notice it has a slope of 1. I go over 2, up 2. All right. And it crosses the y-axis at negative 2, so it's 1x minus 2. All right, the area that we're calculating here is a triangle, and the base is 2. The height is also 2 because this angle is 45 degrees. It's a slope of 1 over 2 up 2. So this is 2, and so remember the area would be 1/2 base times height, which is going to be 1/2 2 times 2, and that's going to be 2. Our definite integral, the value of our definite integral, did give us this area. Let's take a look at another example. All right, in this case, we're going to calculate the integral of the same function, but on the interval from 0 to 2. And so let's see. So remember how this works. All right, the definite integral from 0 to, I'm sorry, not from 0 to 2, from 0 to 4 of x minus 2 times dx is equal to, well, two steps. First, take an antiderivative, x to the third, x to the second over 2 minus the 2x is 2 is the derivative of 2x, so its antiderivative is 2x. And now I'll evaluate it from 0 to 4. And so let's see, so what will this be? Okay, well, we evaluate it first at the upper limit first, always upper limit first. That's a mistake students make. So 4 squared divided by 2 minus 2 times 4. And then we evaluate it at 0. 0 squared divided by 2 minus 2 times 0. And of course, remember this was 4 times 4 is 16, divided by 2 is 8, minus 2 times 4 is 8. So 8 minus 8 minus, this is going to be 0 squared is 0, divided by 2 is 0, minus 2 times 0 is 0. So this would be 0 minus 0. The value of this definite integral will be 0. Let's take a look. Let's take a look. Notice in this case, all right, we can see, all right, that we have 2 units of area from before above the x-axis, so that would be, the integral treats that as though it were a positive 2 units of area. 2 units of area below the x-axis, so the integral treats that as though it were a negative 2, and negative 2 plus positive 2 is 0. So this fundamental theorem of calculus, again, deals with the definite integral just as we had done before. Okay, let's take a look at this integral, the integral from 0 to pi over 2 of cosine of x. Okay, so, and by the way, this I think is one of the more interesting things in mathematics, how this integral turns out. So remember 2 steps. First of all, we have to calculate an antiderivative of cosine. So we have to, who has cosine as its derivative? Well, of course, that's sine. Sine of x is the antiderivative of cosine because the derivative of sine is cosine. So I've taken the antiderivative, but I haven't evaluated, so we're in the square brackets, 0 to pi over 2. Okay, so let's see. So now we have to evaluate this. So we have the sine evaluated at the upper limit first, sine of pi over 2 minus the sine of 0, and the sine of pi over 2 is 1 minus the sine of 0 is 0. Think of the graph of sine if you need to. All right, sine starts out at 0. At pi over 2, we're up at 1. So sine of pi over 2 is 1, sine of 0 is 0. All right, and notice what we have here. All right, we have that the area under this is 1. It's precisely 1. The area underneath cosine, all right, from 0 to pi over 2 is precisely 1. Okay? All right, so that's to me it seems like it would come out to be something involving pi or something like that. That would be my first guess, but no, it's precisely 1. Let's take a look at this integral. All right, the integral from 0 to 3 pi over 2, and let's make a guess at this. Remember, we saw that this much of cosine, this area under the cosine curve was 1. And notice if I look at this, I have 2 pieces just like that, but they're below the x-axis. So this would be -1, -1. I would expect that the value of this definite integral to be 1 minus 1 minus 1, -1. So let's check it. Integral from 0 to 3 pi over 2 of cosine of x times dx, all right, is equal to 2 steps. First step, antiderivative. Who has cosine as its derivative? That's sine. Okay, sine. I was wondering whether I started the recorder or not. From 0 to 3 pi over 2. Okay, and that would be, let's see, sine at 3 pi over 2. Sine at 3 pi over 2, well, remember the graph of sine, all right? Starts at 0, pi over 2. It's up here at 1. Pi, it's back at 0. 3 pi over 2. It's down here at -1. All right, this is a graph of sine, something like this. And sine is that antiderivative that I'm trying to evaluate here. So 3 pi over 2, I'm at -1. Minus, that's a sine value at the upper limit, minus the sine value at the lower limit. And again, as we saw, this was -1 minus sine of 0 is 0. And it's -1, just as we predicted it would be. Just as we predicted it would be. Now, this is really an amazing thing with all the ups and downs about this, all right, that the value of the antiderivative just at 2 places, all right, just at 2 places, somehow keeps track of all the zigging and zagging that a function will do, and we can calculate the area just by looking at the antiderivative at these two places. Let's take a look at another one. The definite integral from 1 to 4 of square root of t times dt. Okay, so we evaluate that, and I'm going to write this as t to the 1/2, okay, dt. Okay, square root of t is t to the 1/2. When I anti-differentiate it, I get t to the 1/2 plus 1. 1/2 plus 1 is 3/2. All right, divided by 3/2, or times the reciprocal 2/3. So this would be an antiderivative. Remember, I don't have to worry about the constant, and now I'll have to evaluate it from 1 to 4. So I'm first of all going to have to take the value of this at 4. So this would be 2/3 times 4 raised to the 3/2 minus 2/3 times 1 raised to the 3/2. Okay, so let's see, to raise something to the 3/2, well, the half means I'm taking square root. Square root of 4 is 2, and then I'm cubing it. 2 cubed is 8, so I'm going to get 3/2 times 2/3 times 8 would be 16/3 minus, all right, 1 to the 3/2, take the square root of 1, that's 1, raise it to the third. 1 to the third is 1, so that would be minus 2/3. And this would be, and 16/3 minus 2/3 is 14/3. 14/3 is 4 2/3. And so look at what we have here. The area under enclosed here by the curve square root of t, and from 1 to 4, and the x and the t-axis, I guess I should say, is 14/3 square units. All right, another example. Let's take a look at the definite integral from negative e to negative 1 of 1 over x dx. So let's see, integral from negative e to negative 1 of 1 over x dx is equal to, well, let's see, who has 1 over x as its derivative? Well, the natural log of x does. That's not defined for these negative values. Remember that x, also the natural log of the absolute value of x has that. All right, so the antiderivative of 1 over x is the natural log of the absolute value of x. If you know x is positive, which it's not here, we're going from negative e to negative 1, negative 2.7 approximately to negative 1, then you could, if you knew x to be positive, you could forget about the absolute value bars. But we need those, and now we're evaluating this from negative e to negative 1. First step, antiderivative. Second step, evaluate it. So we'll have then the value at the upper limit, the natural log of the absolute value of negative 1, minus at the value at the lower limit, the natural log of the absolute value of negative e. This would be the natural log of 1 minus the natural log of e. The natural log of 1 is 0, and the natural log of e is 1. So this would be 0 minus 1. It would be negative 1. Remember, a negative definite integral means we have area below the x-axis. All right, and here it is. The area of this from negative e, negative 2.18 approximately, 28. All right, is where e is, or negative e. This area is, there's 1 square unit of area here. Take a look at another one. All right, the antiderivative, the definite integral from pi over 4 to 3 pi over 4 of cosine squared, cosecant squared of x times dx. Well, this is going to be, all right, the integral from pi over 4 to 3 pi over 4 cosecant squared of x times dx. Well, let's see. The negative cosecant squared is the derivative of cotangent, so this would be the derivative of negative cotangent. Cosecant squared would be the derivative of negative cotangent, and I have to evaluate that from pi over 4 to 3 pi over 4, and that's going to be, all right, the opposite of cotangent at pi over 4 minus the opposite of cotangent at 3 pi over 4. Oops, the other way around. Upper limit first. I've been telling you to do that. Upper limit first, lower limit second. All right, and if we look at that, at pi over 4, just in a right triangle, maybe let me move this up a little bit because I want to add more to the drawing. Pi over 4, remember, is like 45 degrees, so the adjacent and the opposite will be the same. The adjacent and the opposite will be the same, and cotangent is adjacent divided by the opposite, so this is going to be the opposite of, say, 1 over 1. These will be the same, so this will be the opposite of 1, okay, minus, and then in the second quadrant, this is where, right here, if we embedded this angle in the second quadrant, we'd have the same thing, but this would be the angle 3 pi over 4. And now we're going to have, say, a 1 for the rise and a negative 1 for the run. So this would be the opposite of a negative 1 would be the value of cotangent. Cotangent is negative in the second quadrant. So notice that this is going to be 1 plus 1. This value would be 2. And here we have a little picture of it. This is cosecant squared, okay? And the area underneath this curve from pi over 4 to 3 pi over 4 is 2 square units. I have one more example that I'd like to show you, all right, and that is this one. Okay, the integral from negative 1 to 1 of 1 over 1 plus x squared times dx. Now you have to remember, who has 1 over 1 plus x squared as its derivative? Well, that's tan inverse. So this would be tan inverse of x. You have to remember all those. All right, from negative 1 to 1. And so if I evaluate tan inverse at 1 minus the value of tan inverse at negative 1, well, tangent, what angle, all right, so we're asking what angle has a tangent ratio of 1? Tangent is opposite over adjacent, and that's going to be pi over 4, just like it was up above. And what has, so that would be here like this, in this portion, okay, pi over 4, okay, 1, 1, so this would be pi over 4, and for the interval that tangent is on, that has an inverse, all right, this one would have a negative 1 over 1, and that would be negative pi over 4, so minus a negative pi over 4, and pi over 4 minus a negative pi over 4 is pi over 2. So the value of this if this definite integral is pi over 2. So this area underneath, this is a graph of 1 over 1 plus x squared on the interval from negative 1 to 1 is pi over 2 square units of area there. Okay, so there are some examples of definite integrals.